RE, the height will become 6 RE. This is how high the satellite has to be in order to be in the geosynchronous orbit. Next, let's learn something which is slightly different. That first of all is the gravitational field. Imagine we have a large mass of m and we have a small mass of little m, and obviously we know that the large mass will attract the small one. Well, certainly the small one also attract the large one, but right now we're interested in the small one. So the gravitational force on small one is Fg, that follows Newton's law of universal gravitation. Well, if that we define gravitational field, that is a vector, has a symbol a little g, that's a vector, equals to gravitational force divided by the mass of this particle, then we will come out as, if this capital M is a spherical symmetric mass distribution, then we can assume this is concentrated center. So if we know the separation of R from the center of this guy to the point mass M, we have this gravitational force equal to capital G, mass m, little m over R squared divided by little m. So we'll get that. That is obviously the magnitude, and the direction should always point to the large mass m. This is called centripetal, which means center seeking. So that's why when the little m is here, it's center seeking. And you can imagine if you have a little m right here, and the direction of gravitational field will be toward the center of large m. A field, gravitational field, means that the test mass is in the area that will be affected by the gravitational attraction of this capital M. That is just a concept. However, the very useful thing mathematically that we're going to learn is the next one is gravitational potential energy. Now, we learned from previous chapter that a potential energy should connect to a conservative force. The definition of conservative force is that force, if there's a particle and there's a force on this particle, if that particle moves a distance dr, and this symbol means you finish a closed path, you start from point A, you go somewhere, you're back to A, that's closed path. If this integral comes out equal to 0, then that force F is a conservative force. Very weird definition. Well, that is from your for survey book, that is chapter 8, definition of conservative force. A conservative force will associate with a potential energy. So you see, if we have this called gravitational potential energy, therefore that indicates that gravitational force is a conservative force. I am going to prove that. First of all, let's look at the situation. If this is Earth, and mass of the Earth, assume it's at the center, and we have a particle right here of mass little m. Initially, it is located at point A, and under the influence of gravity of Fg, initial position vector is r of I. And then if this particle somehow moves to position B, and this is the passage, and well, at position B, gravitational force still be center seeking, so that is the direction towards the center of the Earth. And final position vector is r of F. Now, we're going to look at this case and to see how can we prove that the gravitational force here, Fg, is a conservative force. There's something very interesting that I want to point out. When a particle of mass m starts from A, if it has to move tangentially with a little distance called d of s, that's two-dimensional displacement. Any two-dimensional displacement can be split into that of, this one is, let's say, is center seeking, it's around the radius direction, and the other one is the tangential. Now, ds is tangential to the path, but this part is tangential to the radius because that is the radius of r of initial. So, which tells us that any of ds, which is like that, can be split into that ds of this and ds of that. That is called ds of radius. That's called ds of radius and ds of tangential. Okay, let's continue. Work done defined as f dot ds, force dot displacement from point A to B. So let's say this is Earth, and that is a particle of mass m starting from point A goes to point B. And I explained that any ds tangential to the path can be split to the ds of radius direction of ds of tangential to radius direction. So we have the ds equals to ds of r plus ds of tangential. Okay, so let's take a look at work done equals to, if it's A to B, of f dot, we'll replace ds by ds of r plus ds of tangential. Be careful, both are vectors. Now, in this case, the force is always center seeking because that is gravitational attraction force. So that is opposite direction of the radius. So when we have gravitational force F dot that the ds tangential, that will come out 0 because the angle between gravitational force and tangential direction is 90 degrees. A dot B, if AB has a 90 degrees angle, that equals 0. So the result will have this gravitational force F of G dot ds of r left. Now, since gravitational force is center seeking and dsr is radius direction, so when they dot, the angle is 180 degrees. So, I'm sorry, when they dot, it is a cosine. So, AB cosine 180 is a negative sign. Negative, and we're going to plug in the magnitude of gravitational force, which is G between mass of the Earth and mass of that point, divided by the separation square, and since this is the radius direction, that is simply dr. Okay, as we can see that these are constants, and we can pull this out of it. So negative A to the B, well, we can move the constant out of this. Well, this constant is the combination of constants right there. And then divide by r squared is r to negative 2 of dr. So the result is negative of constant, well, comes out. And the integral of this will be negative 2 plus 1 as denominator, and r to the negative 2 plus 1 from initial r of initial to r of final. So if we look into this result, this negative, that negative cancel. We have g m e of m, that when we have this 1 over rf minus 1 over r initial. Now let's take a look. If we start from A, it goes to somewhere, but eventually come back to A. Isn't that true? Our final initial positions are the same because we finish a complete passage. When that's same, then this will be 0. So work done by gravitational force for a complete passage equals to 0. Conclusion: gravitational force is a conservative force. This is what we just got. Work done by gravitational force equals to that. Now, if work done by a conservative force, that according to what we learned should equal to the negative change of its potential energy, and change means potential energy final minus potential energy initial. So what does that mean? That means that if we look at in the final minus initial, there's a negative sign. If we move this negative sign to the left side, what we have is, as a matter of fact, is negative of G M E M over R final, because this negative sign gets here, minus, negative sign getting here is plus, but minus a negative is plus. That is G M E M over R initial. What does that tell us? That tells us that final potential, which has this expression, initial potential, which has this expression. So potential energy, gravitational, has expression negative G M E M over R. What is R? Well, that is the position vector, that the little m away from center of the earth. This should be able to apply to any two particles has a separation of R. So it's G M1 M2 over R. Or this can be applied to spherical symmetric objects. Then you can assume the mass concentrated at the center of spherical distribution. So gravitational potential is a negative thing. And also, please notice when R equals to infinite, what does that mean? That means when a particle is infinite away from another one. If M1, M2 has a separation of infinite, then U equals to 0, which means when an object is infinite far away from another one, the gravitational potential energy is 0. Let's think about this. Somehow, one particle step into other particle's gravitational field. We just learned that. So it will be affected by the gravitational attraction force. And then if there's force, there will be acceleration. So the particle will speed up, or we say simply move towards the attraction of the center. Now, when the object speeds up, it picks up kinetic energy. However, well, if only between two particles, the only force is gravitational force, then the system's mechanical energy is conserved. If a particle picks up kinetic energy, then, well, it has to lose from something. Then what happens is the total mechanical energy is kinetic plus potential. If it's a constant, then initially that when a particle is infinite far away, that U equals 0. If this is 0, and then if kinetic energy initially is also 0 because the particle does not move. Now, eventually, if this becomes positive, then this must be 0. But this must be negative, I'm sorry, because that constant is simply 0. When two particles are infinite away from each other, the potential energy is 0, the kinetic energy is 0 because they do not move. 0 plus 0 equal to 0. When Ke becomes positive, U has to be negative. That is why potential energy has a negative sign. So let's talk about energy. Let's have energy consideration about planetary and satellite motion. Imagine that this is Earth, and that is the radius of the Earth, and we have satellite, which is h meters above the surface of the Earth. That's a satellite. And so the definition of its radius is that radius of the Earth plus the altitude h. And if it's in the circuitry orbit, the tangential velocity is v. The total energy of the satellite, E, equals to kinetic energy plus its potential energy. Kinetic is 1/2 mv squared. Potential energy is negative of, that is the Earth. So it's mass of the Earth as it concentrates the center, and has a G, and a mass of the satellite. And then we have this R square. No square. That's potential energy has no square. Okay. On the other hand, the reason the satellite rotates around the Earth is because of gravitational attraction F of G. Gravitational attraction between the Earth and the satellite follows this Newton's law of universal gravitation. That equals to the mass of the satellite, because that's a force, times a centripetal acceleration. That centripetal acceleration is v squared over r. Now the left side, as right here, is capital G, mass of the Earth, mass of the satellite, over r squared. Now if we look at 1/2 of msv squared, which is what we need, because the kinetic energy here is the kinetic energy of satellite, so it's 1/2 msv squared. Obviously, we can cancel 1 over r. So kinetic energy of the satellite can be replaced by capital G, mass of the Earth, mass of the satellite, over r. So we have that capital G, mass of the Earth, mass of the satellite, over of r. And on the other hand, because initially we have this equals to that, this 1/2 we time to the right, we should also time 1/2 to the left. So that should be like this. And then the second term is a minus of G, mass of the Earth, mass of the satellite, over r. So if you look at it, you can view this as 2 over 2. So the result is negative of G, mass of the Earth, mass of the satellite, over 2r. That is the total energy of the satellite in a circular orbit.